Okay, today we're going to start our module 4, the inverse kinematics. This module is going to be a little bit different from what we're calculating in the previous two modules. In the previous two modules, we kind of use metrics skills to do everything, but this time we do not use a lot of metrics to solve for the requirement of inverse kinematics. Instead, we're going to use a lot of triangular functions to generate the result. So let's get started. But before we actually get started, let's review what forward kinematics is talking about and what's the review, what is the inverse transformation, so that we can have better understanding what's going on. So first, let's review what's going on. So in our configuration, we are having rotational movement. And before we start, we always attach coordinate system to the specific components. There are two kinds of components we have in the module we talked about last time. One is rotational joint. The other one is linear movement joint. So with those two kind of joints, we have everything. We can describe almost every movement we desire. However, before we actually attach the coordinate system, let me remind you, the coordinate system has its special rule, which is right-hand rule. Right-hand rule means that the direction of coordinates are kind of fixed. So we always want to use our right-hand rule to determine what is x, what is y, what is z. So this method is handy. Please keep in mind or keep this figure somewhere so you can every time you see a new coordinate, you have some kind of idea how it's going to be rotated. So before we start, we know this one is going to be z, and this one going to be x, this one is going to be y. You might see that, well, I have x1, y1, z1. Is this follow going to be is this rule going to be followed by every coordinate system? The answer is yes. It doesn't matter you are dealing with robotic system or you're dealing with animation. This is always a rule we're going to use. So let's talk about what kind of a coordinate system we are going to use over here. So before we start to do the attach the coordinate system to this specific rotational joint, we need to know that the rotational side, just like what we do in a two-dimensional plane, so it's going to be always point out to the paper or point into the paper, which means this direction pointing out, this one over here is always z. And we attach our coordinate, our right-hand rule into the system, so you can see if I have the z up to this one must be x, this one must be y. So if you put your hand if you have your orientation of your right hand with the three-dimensional I just draw on the sides, you're going to determine this one is going to be x, this one is going to be y. Okay, and there are four parameters we're going to describe between two joints, and those two joints must have some kind of rigid body linked between that. That is our link. So every time we're going to put a table and we put our link number 1, 2, 3, and four parameters. The first one is theta and di. Those two are related to z direction, and we also have ai and alpha I. Those two corresponding to x direction. So those two are something you need to remember all the time. And since we know it's related to z direction, it is going to be something like this. And this is going to be my theta. If you attach another coordinate system another joint over here, the distance between this one and the root of this one is going to be my d. That you should put over here. Now, those two are the responding to z. Sometimes, if you need to do something, determine another coordinate system to the second joint over here, let's say this point is not, not, not. So this must be not. So I'll have this one over here, this one over here. So since this one is from this angle, put to this angle. So the rotational direction is about x-axis. So this one over here is going to be my x1, and this one is going to be my z1. And use our right hand rule, we should be able to determine that the y1 direction is actually point to this direction. Okay, so theta in this direction, in this component over here. Now alpha in this table over here is going to be the angle between this z0 and this z1. So in this case, it is going to be 90 degrees. But depending on how you rotate everything, since we're doing something like this, we actually rotated that to negative 90 degrees. So this is something you need to know. And the origin is not shifted in x direction. So in this case, A0 over here, A1 over here is going to be 0. So that is something you might need to remember, how to determine all the coefficients. Once you determine all the coefficients, then we can start to do our rotational conversion. So there are four matrices you need to know. We use a specific formula, A. That is my transformation matrix from I frame to I plus 1 frame. So in this case, we're going to have rotational matrix. That is my Z in theta I. That is going to be I. Then the second one is going to be translation matrix corresponding to Z and DI. And the third one over here is going to be translation as well, but this time it is going to be X, AI. Then I'll have rotational matrix X, alpha I. Keep in mind the sequence is important. You need always follow this specific sequence. If you swap them, you're going to have some kind of different orientation after you do your calculation. That is not something we desire. So keep in mind this is something you need to do. Now, when we are doing something like this, this is going to be the transformation matrix. You might be confused. Okay, in the previous several modules, we are talking about rotational, translational, but sometimes it's 3 by 3, sometimes it's 3 by 1, sometimes it's 4 by 4. What is that? So when we are combining those kind of things, if you are dealing with just pure rotation, then it's going to be 3 by 3 because you have only three angles in terms of x, y, and z. So you're going to have 3 components in x direction, 3 components in y direction, 3 components in z direction, which means you're going to have a 3 by 3 matrix when you are putting everything all together. But when we are dealing with translation, if it's rotational joint, certainly you're not going to have rotation. So if you are dealing with the vector regarding to the displacement in a rotational joint, certainly it's going to be 0, 0, and 0 in x, y, and z directions. But if you include those 3 components into the previous 3 by 3 matrix, you're going to have something like 3 by 4 because there are 3 additional components added into the system, which means the transformation matrix we're looking for is R and D. This one is my rotation. This one is my displacement. To make everything feasible, you're going to add 0 over here and 1 over here. So after we configure all the rotation and displacement in the transformation matrix, then we're going to start to put everything all together. Keep in mind the equation we have is in a specific sequence, and you cannot change the order in the sequence, because if you change the order in the sequence, the orientation is not going to be correct, and the direction of each axis might be minus, or what's worse, it might be in another direction. So keep in mind when you are using the formula, the sequence is important. And let's repeat the formula again. The formula is going to be A equals to, first we're going to have rotation about z-axis, and we're dealing with zi. Let's use I over here because it must be corresponding to the I-axis as well. Then the second one is going to be the translation. That is still along z-axis, but this time is going to be di, the distance. Then the third one is still translation, but this time with translated about along x-axis, and we're talking about ai, the distance between two joints. And the next one is again rotation about xi, but this is alpha I. Normally this one over here is the angle between zi and zi plus 1. So those things are important. And when you are dealing with those kind of things, the equation is actually, let's put it over here, so I'm not going to use up all the space. So the rotation about zi, it is going to be cosine theta 1, sine theta 1, negative sine theta 1, cosine theta 1, and 0, 0, 1. Those two components are 0 as well. This one is just rotation, and since we are talking about the rotation matrix, we do not have any displacement. Therefore, the three components over here are going to be 0, 0, and 0. And in the bottom over here, we just fill in the numbers 0, 0, 0, and 1. For the second one, it's pretty straightforward because we do not have any rotation, so it's going to be identity for the rotation matrix. But we do have some kind of displacement along di, so it's need to be 0, 0, and di over here. Keep in mind this must be the z direction because we are moving along z direction. Then the other three components is nothing but 0, 0, 0, and 1. The third one is still rotation. Still, we're going to have identity matrix as a rotational matrix. Then we have three zeros over here. Over here, we do have displacement, but this time it's along x-axis. So AI must be at this location. The other two components are 0 because we do not have anything at along y and along z. So this one over here must be 1. That is going to be my third matrix. The last matrix, this becomes a rotational one, and it is going to be about x-axis. So put 1 over here and 2 zeros over here, another 2 zeros over here. Then this one is going to be cosine alpha I. It's negative sine alpha I. And it's going to be negative sine alpha I. This one over here is sine alpha I. And this one is cosine alpha I. We do not have any displacement, so 3 zeros over here. The bottom row is the same. So this one over here completes our transformation matrix. and we are going to use this one to calculate for the forward kinematics from the first joint till the end of joint. But when we are doing something like this, we would need to know the 4 parameters over here for each joint. If you fail to know some of them, you cannot estimate what the position of your end effector in the end of a robotic device. However, if we try to do the reverse, there is no guarantee of something like that. When we are using forward kinematics, what we really want to do is to, given the values of joint variables like zeta, alpha, and dA, then we need to find out the destination or the end position of the robotic device. So we can have, let's say, 3, 4, 5, 6 joints or links. Then we can still find those kind of things if all the coefficients are given. But in this case, if you have, because we have 4 variables at each joint. So if you have like 6 links, then you're going to have 24 coefficients, even though a lot of them are going to be zeros, but we still need to have all the informations. However, if we are using inverse kinematics, then it means that we try to find, by given the position of the end effector, then we try to identify all the coefficients at each joint. Is that possible? Sometimes it doesn't. If you have more than, we all learn linear equations. If you have 3 unknowns, you must have 3 equations to solve. If you are having 6 links, it means that you're going to have 24 variables you need to solve, even though some of the joints need to fulfill certain kind of criteria. But overall, you still need to solve at least like 10 or 12 unknowns, which is not somewhat. You would need to have 10 or 12 equations to come up with all those variables. It might not be feasible because even though you have 10, 20, even though you have 10, 12 equations, the problem is the equations are not linear ones because cosine and sine, or tangent, those kind of triangular functions, we do not consider they are linear. When they are not linear, it is very unlikely you can inverse the matrix and try to identify those kind of variables because it doesn't work. So when we are using the inverse kinematics to come up with all the answers, it is tedious and most likely it's going to be case by case. So when we are dealing with inverse kinematics, there is no good universal algorithms to produce the inverse kinematics of a series link manipulator, and generally we are using geometric interpretation to identify the angles or displacements of each joints. And we also need to decouple the rotation and translation from the transformation matrix into individual ones so we can identify how are we going to analyze for the angle or for the displacement. And also, rotary and linear movements are restricted by physical limits. For instance, you use your arm and you are designing a robotic device, which is I think we have an assignment in module 2 that is talking about this kind of problem. So if you are designing a robotic device for human arms, then the joint of between your forearm and upper arm and lower arm, it is not 360 degree. You can actually see if this one is 0 degree. If you move this up, you can go up to about 150, 160 degrees only because that's a limitation of human being. So when you have those kind of considerations, you also need to embed those kind of restrictions into your design. You cannot say, okay, I want to have a robot that is wearable and I can move the arm like 720 degrees. It is not possible because we're dealing with human being. Even though your robot is capable of doing so, but human being cannot do that. So you need to keep in mind those kind of things are something important to us, and we always need to ensure what are the restrictions and whether they are linear or nonlinear when we try to solve those kind of equation or variables. Those are something important. In addition to that, when we are dealing with inverse kinematics, two important mathematical skills are law of size and law of cosine. I believe you guys learned this thing in statics, dynamics, and many other geometry classes. Let's do a little bit review. So if you have a triangle like this, if you apply law of size, the lengths over the side value, they must be equal. This is handy and it's very commonly used. If you try to use law of cosines, that's another method we always use. These are the very common equation that we're going to use. In addition to those two, we also deal with if this is a right angle and this is R, S, T, this is theta. Tangent theta is going to be S over R, or theta is going to be arctangent S over R. So this is also handy when we are dealing with our calculations. Triangular relationship is a very important tool that we're going to use for this class. So keep in mind, if you need to have those three tools remembered, then if you cannot remember that, you might need to keep those formulas handy so you can find the equations all the time. Okay, the next part we're going to talk about examples.